In today's lesson, we're going to look at the differences between linear, quadratic, and exponential functions. Let's look at linear first. Remember, linear is just a fancy word for line. So I'll know my scatter plot, my data points make a linear function if they are forming, if they're trending in a line. The line of best fit for this will be y1 approximate to m times x1 plus b, which is just a fancy way of saying y equals mx plus b. We just change out the equal sign for approximate because the line in the data in this graph, as you see, is not a precise line, but it's close, it's approximately to that line. So let's write down our differences here. Linear is definitely going to be data trending in a line. So the data we were given is trending in a line. The data we were given here was temperatures in degrees Celsius. As that increased, so did sales. So we have a constant increase of rate. So increase, you can also have decrease too. So just because your line's going the other way still could mean it's linear because it's a line. So it increases or decreases at a constant rate. You're thinking about adding or subtracting those y values, like we were talking about last lesson. So that's going to be the differences among linear. So we're going to be adding or subtracting, increase or decrease at that constant rate. For quadratic, we have our curve of best fit. So right off the bat, you have a curve, not a line, and the curve of best fit is y1 approximate to a times x1 squared plus b times x1 plus c. When I look at this data here, so here's my points, I'm not going to have a perfect line here. Because if I drew a line, or I drew as close as I could through all the points, I'm still missing some other points. A line of best fit does not work here, so I'm going to get rid of that. It has to be a curve of best fit. So it's just like our standard form, but we have an approximate instead of an equal sign again. So again, above here, what I'm circling now is what you can type into Desmos to get the exact curve of best fit. What helps me remember for quadratic is that the data is going to be making a parabola a U shape. So I either have a smiley face down kind of shape, like here, or I could have a smiley face up kind of shape. What I think about for our quadratic functions is that you'll have an increasing part and a decreasing part. That's going to be different than any of these other functions here. You're going to have an increase and a decrease. So it goes up at one point, peaks at the top, and then comes back down. How I think about it is think about throwing a ball to a friend. So I have my ball over here and I'm throwing it to a friend over here on the other side of the field. What happens is when I throw the ball, it leaves at a certain point. It's going to hit a peak height of my throw. Then after it's at the peak height, it's going to go back down so that my friend can grab it in his or her hand. So that's going to be kind of what you're thinking about for quadratic. Think about the data making that kind of function the same path it would make if a ball was thrown. Or you could throw a ball under 2 and back up. For exponential, we have a curve of best fit again. So again, if I draw a line through this, would not be best fit for the data because I'm missing all of these points above here. I'm not including all my data, so a line would not work here. So let's get rid of that and think about an exponential curve of best fit. That means we have y sub 1 approximate to a times b to the power of x. That's going to be our standard form for exponentials, just like we've seen before. Again, we just put the approximation sign on Desmos to help us out here. What we're going to do is we're going to talk about what's different between this and quadratic. So we already know it's not linear, it doesn't make a straight line, but what makes it different than quadratic? Well, first of all, it doesn't have an increase and decrease. It's constantly increasing here, because as time and minutes happen, so does temperature in Celsius degrees. Think about you're heating up a pot of water on the stove. It starts at room temperature, and then after time goes and increases, it's going to get hotter and hotter and hotter, building off the already previous temperature it was at. So what happens in this case is you're going to be multiplying. You're not adding or subtracting, you're multiplying. So that temperature of my water is going to increase exponentially. It's not going to increase, oh, I'm adding 2 degrees every minute. No, it gets warmer and warmer and warmer and warms up faster as well. The rate will go up faster too, so there's not a constant rate. Not a constant rate for boiling your water. How we know there's not a constant rate on this graph is that we're going to vary in steepness. This graph varies in steepness. What that means is, take a look. These data points are pretty close together. They're still getting multiplied up, but they're pretty close together. Whereas these points on our graph, these data points, are more spread out. They're increasing and making the graph steeper. My slope would be steeper here than at the first part of my graph when my water's just starting to boil or starting to heat up. That is our case and our differences amongst the three. Now we're going to take a specific and special look at linear functions here. We have the same graph we had on the front. Let's label our axis. The temperature is going to be x, remember, because x is always the horizontal axis, and our sales in dollars are going to be the y. And specifically here we're going to talk about ice cream sales. So what this graph is representing and shows is that as my temperature increases, so does my sales of ice cream. Makes kind of sense, but we want to kind of predict and see the line of best fit. So right away, I'm definitely going to have a line of best fit. There's no curve to my data. There's no increase and decrease like quadratic back here. And there's no kind of change in the steepness. It's kind of moving at a constant rate, makes a perfect line, not a curve. So what I do is go to Desmos, pull up Desmos, I have my data all in here, and I type in that equation, that exact one I was talking about. Y sub 1 is approximate to m times x sub 1 plus b. Awesome. So that's going to give me this line here. What I need to write my line is the slope m and my y-intercept b. So I go back here and write y equals, or y is approximately equal to, more specifically, 30.0879 x plus, we're going to have our y value now I want to put in as well because I'm always replacing the m and the b when I'm writing this slope-intercept form. I have negative 159.474. So I got negative 159.474. I can get rid of this plus sign here because it is subtraction. Don't need a plus and a minus together. That's going to be the line of best fit. So that's going to best represent this data. It's talking about my y-intercept being at a negative number, which is not truly practical for this application, but it's the line of best fit. And my slope is 30. So that means I have a rate of 30. So that means ice cream sales over temperature is going to be a rate of 30. When I estimate the sales at 23 degrees Celsius, that's going to be my x value here. Temperature Celsius is on my x-axis, so I know I'm looking at 23 on this x-axis. Well, I can go up to my line of best fit and predict if you want to do it that way. But the best prediction is going to come from writing this equation. So I'll go back to Desmos to help me out and type in my equation. Y equals 30.0879x plus, well, or minus, that 159.474. What I can do now is replace x. It was at 23 degrees Celsius, right? Well, if I replace that 23 for x, which is my temperature in this case, I get $532. and it was 0.54. So about 0.55. Makes most sense when we're talking about dollars, having two decimal places. So that's my best estimate. The last question is asking us what is the best prediction of sales at 29 degrees Celsius. So again, I'm plugging it in for X, not Y. I would know if I was plugging into Y if they gave me my dollar amount, if they gave me something that would be relevant to my Y axis. But this is talking about degrees Celsius again, so on my X axis. Now for this one, 29 would be off my graph over here. I don't quite know. I can make a prediction with my graph and extend my line, but I don't quite know exactly where it's going to be. So I go to Desmos again, and instead of typing in 23, I type in 29. That's going to be giving me Y equals 713.10 if I round it up. So that's going to be my answer for dollars. What's that saying? Let me just go back to make sure I got the correct answer. Yep. What that's saying is when my temperature is 29 degrees Celsius, my sales will be about $713.10. That's what it is looking like here when we have a linear model. We have that constant rate, that data trending in a linear pattern, a line. That's the real main differences for our linear function.